Error Correcting Codes by Daphne Evans.
Looking back to the childhood game of telephone, we realize that messages will always be susceptible to change. In a world of satellites communicating with each other, email, and information sent through the internet, errors in those messages are bound to happen. Our goal is to recognize when an error has happened and to correct it in order to restore the original message and content. In order to correct an error, we first need to send a message. Each message we send is called a code word. In the examples we will highlight, those words are a string of either zeros and ones for binary messages, or A, C, G, T, or U for DNA and RNA. Both types of code words contain important information that will be lost if the error is not corrected. In the case of error correcting codes, we are assuming the length of each code word remains the same, as only values in the code word will be changed. We know an error has occurred when we receive a word that is not part of the agreed upon code. If we agree on the set C as all possible codes, yet we receive 0, 0, 0, 0, 0, 0, or 6 zeros in binary, we know there is an error somewhere. Since those 6 zeros differs from an agreed upon code word by only one place value, and if we know the message only has one error, we know the original code word was 0, 0, 1, 0, 0, 0. This thought process is captured by the use of the Hamming distance. The reasoning we just used to correct an error in the word received relies on using the Hamming distance. The Hamming distance is the number of places between two words that are different. We will look at the original code word sent and what word was received compared to our agreed upon code on the next slide. We're going to be using the notation capital D for distance, the lowercase h for Hamming, and then x and y are the two words that we're comparing to see how many places are different between them.
An example is C. C is our code word. It has 4 different code words within it, but it's our code set. And we compare those sequences, we can find the Hamming distance. So for the first two, we can see that first place value is 0 and a 1. Those are different, so our Hamming distance has at least 1 in it. Look at the second place value, they're both zeros, so that does not contribute to our Hamming distance. And then the next 4 ones are all different. One's a 1 and a 0, the other ones are all 3 zeros and then 3 ones. So if we go through each pair of these two, rearranging them, but comparing each pair, we get the Hamming distances of 5, 4, 3, 3, 4, and 3. The key here is to know the minimum distance between any two of these code words is 3. Since we want to minimize our errors, it's nice to know the minimum distance is 3.
Let's look back at the original code word we were sending, the word we received, and the set of possible code words that we received could have been. First off, we know that there is an error in what we received since it does not match any of the agreed upon code words. We also know that when comparing any two of the original code words, they will not differ in less than 3 places from each other. If there were 2 original code words that both did differ from our received word by 1 place, then those 2 code words, since Hamming distance compares 2 words at a time, will be within 2 of each other. This is impossible since the minimum distance between any 2 of our agreed upon code words is 3. So there are no other words than the original that our word could be. Since this is section 5.2 in the chapter about metric spaces, we can imagine the Hamming distance as a way to create balls around each code word with the radius r. Each ball contains all the words that can be corrected back to the original code word, around which the ball is centered. The 4 code words on the right are as they should be, with the minimum distance between any 2 code words being 3. The 4 code words on the left, however, show the impossibility of any word being 1 away from 2 code words at the same time. Note the drawing is not to scale. Also, since this situation is impossible, no drawing would be to scale. The vertices on the right-hand model are all at an agreed-upon code word, while the upper left vertex of the left-hand side is at a word that was received, has an error, and is originally from that upper left code word. We want to correct the word back to its original code word. If it really was a distance of 1 away from 2 code words at the same time, then those code words would have to be within a distance of 2 from each other by the triangle inequality. Since any value less than 2 is less than 3, it contradicts the minimum Hamming distance that we know is 3. Thus, there is not a word that we could have received having only one error with two possible code words it could have been.
To reinforce the concept of those open balls, there's a theorem about the number of errors a message can still have, and we can still correct. So a code C of length n is chosen, so its minimum distance is d. Then every message of length n, so C is the whole bank, d is the minimum distance of one of those codes. So we know that any of those codes, whatever the length is, when using that minimum distance of one of them, d minus 1 divided by 2, that floor function has to have that maximum number of errors or less, and we can still correct it back to the original code word. The key to the proof on the next slide is that only one code word can have that minimum distance of d. So on this next slide, we're going to let C be the original code word sent, and F is the message that we get at the end. So we can still take the Hamming distance between, for instance, that blue circle and a code word, the green circle, and we know the maximum number of errors is that floor function mentioned on the previous slide. Suppose again there's a C prime, another code word just like that. So if we add them together and we look at the distance, the Hamming distance between the first code word and the second code word, I know they have to be less than or equal to those opposite two sides of the triangle summed together. Using algebra, you get d minus 1, yet the minimum distance is d. So d minus 1 can't exist. It is smaller than d, so it cannot be a Hamming distance between any two of the code words, which is our contradiction and proves our proof that as long as we have that floor function equation there, as long as we have that number of errors or less, we can actually correct the code. It is nice and convenient to know how many errors we're able to correct for each code word of length n. But what if our message gets lots of errors, such as in the game telephone? Imagine a game of telephone using any word in the dictionary as fair game versus a game of telephone using only tourist language terms or some other type of word bank like Spanish vocabulary. Which one would have the highest amount of errors in the final message? What if both final messages had the same amount of errors? Which scenario would the players be able to fix or correct the final message reliably? Decreasing the possible set of code words increases the amount of errors that can be corrected, which is our solution. It's nice to have a small sample space from that. But is the Hamming distance the end all? No, it's not always the most accurate. It doesn't always show the best relationship between the original code word and our resulting message. For example, DNA sequencing, we have to change DNA into RNA so we can make proteins, amino acids, creating new cells, and other cell processes. The gist in RNA is we take the thymine, the T, from DNA, and we change it to uracil for RNA. This single swap is represented well by Hamming distance because it's simply that one replacement, so it's one place that it's different. But what if we start deleting or inserting things? So if we look at the first string of nucleic acids here, we replaced the T, the thymine, with a guanine, but with a G, guanine. And that's fine. Hamming distance is still 1. But now if we insert a T, a thymine, in between the A and the C, it's shifted everything down, and so now our string of nucleic acids looks a lot different in the Hamming distance world, even though we only added one different nucleic acid. So we're going to use the Levenshtein distance to tell us more about the pattern relationship between the code word and our resulting message. So the Levenshtein distance is taking the minimum of the number of insertions plus the number of deletions plus the number of replacements so we can get X to change into Y. So there are probably long ways you can go about several things of getting one sequence to look like another, but if we take the minimum, that's our Levenshtein distance. So looking at this in application of the Levenshtein distance, we have two strings of nucleic acids. And the Hamming distance for these two, the places where they differ, is 7. There are 7 different places where they are different with different nucleic acids, and then the Levenshtein distance is actually 3. We took that first C, replaced it with a G, inserted another G, and then at the end we replaced that C with an A. So we did 3 different things. We had 1 insertion and we had 2 replacements, so that minimum is 3. The Hamming distance makes it seem like these are really way off base, they're totally different, versus the Levenshtein distance shows us that they're more related than we thought. And so the Levenshtein distance better represents this string of nucleic acids and the message and code words as you go between. So a real application of the Levenshtein distance is spell checking. You want to correct it, so you want to find an error, but then also correct it. Speech recognition, not saying your speech has an error in it, but according to a computer, they're trying to find those patterns and realize what you're trying to actually say. And then plagiarism detection is the only one that's not really correcting it. It's just trying to find the pattern and figure out, did you match someone else's from before? So if you are closer to the original problem, original work of whatever you're working on, then that's a plagiarism. And that concludes error correcting codes.